Hi, welcome back. We're now in chapter 3, which is kind of where the fun starts to get going, because now we really have to start taking a look at fluids and phases, diagrams, and gases. And so, when we talk about phase, really the thing to know is primarily here we're talking about both liquids and gases. And it learned in probably high school physics, a liquid, it kind of sits at the bottom of the glass. It fills a glass, but it sits at the bottom, kind of gravity pulls it down, whereas a gas just completely fills the container it's carried in. But the thing of water, and water can be both a liquid and a gas, and it's going to do it through kind of a phase diagram shift. And so, if you're taking a look at chapter 3, and I'll draw a couple of these diagrams, one thing to note is all of these diagrams really are specific to that particular fluid or gas. I mean, whether it's water, ammonia, propane, all of them will have different phase diagrams, different particular data points. And, really when you think of all this data, I actually want you to imagine like all these poor, grad students and scientists who have sort of gathered all of these data points throughout the years. But as well as there's a lot of this stuff that is then done with really intricate math models of all of the sort of fluid interactions. So, if we take a look at pressure and then temperature, and that you might have a system that does something like this. There we go. And at low temperatures and high pressures, this would be your solid region. So think ice if you're water. And then you can imagine holding that pressure constant and then warming up. And so you would cross over into a liquid region. And then again, if you kind of held that pressure and you kept warming up, you would cross over into a vapor region. And this is going to be true for most systems. But there's a couple interesting points on this, right? There's one here. This is called the critical point. We'll come back to that in a second. Don't show that very well. Let's go see if orange works. So that's the critical point. And then this one's actually called the triple point, because you could, theoretically, if sitting right on that, you could be in a situation where part of your container has vapor and liquid and ice, if you're water. And so when you're above this critical point, you actually are considered a supercritical fluid, and there's some really interesting properties that come along with that. In fact, supercritical CO2 has a whole bunch of uses, including decaffeinating coffee and things like that. And then, honestly, like kind of manipulating the fluid and manipulating the heat, heating it up, expanding it, really all of these thermodynamic processes, it's where we're going to be able to create things like engines and cycles. So it's really interesting. Now, you can take a look at also pressure versus, draw here, specific volume. And because, when you get to this line, if you're a liquid and you get to here, and you've seen this in your pot of water, you don't instantaneously turn into a vapor, right? You actually get to, say, 212 Fahrenheit, and you got to keep boiling and boiling and boiling. You got to keep putting any energy in. And so that amount of heat is required to kind of get through that process, right? That heat of vaporization. And so you can actually see it this way, because what is happening if you took your pot and you actually had a lid on it, and you may, to hold the same pressure, maybe you need the lid to rise, but you're going to see ultimately a dome. So this is a vapor dome. And so you might be liquid up to this point, and then you're going to cross, and then, pressure is going to, constant temperature, and this one's going to go down, mixing that up. And so if you're at this point, you keep warming up all the way across, and that system is going to get less and less dense. Okay? And then the reason I screwed it up is this is not a normal one we usually plot with. Usually when we're looking at domes, I'll draw again here, temperature versus specific volume. Actually, when we get to entropy, usually we look at these domes in terms of temperature versus entropy. But I'll sort of draw it here anyways. And so you might have, and I'll switch colors again, you might have a system at a constant pressure coming in and doing this. And so you would raise its temperature of that liquid, right? This liquid water, raising it, okay, here you go, and here's where you're starting to boil, and then here, all the way along here, and here's where you now turn to all into vapor. And then as you keep adding heat, then you're going to raise the temperature of that vapor again. And so this area here is called superheat. And this is how boilers work. If you're actually if you're boiling water for power generation, you're going to use coal, or you're going to use whatever you might be using. A nuclear reactor is going to do the same thing. You're going to boil that water. You're going to turn it into vapor, and then you're going to superheat it and get it higher up. So your cycle is going to kind of come off of the superheat. And then this line here is called your saturated liquid line, and this is your saturated vapor line. And again, there's your critical point. So, I mentioned last time, a lot of work you end up doing in thermodynamics can be sort of the tedium of calculating the properties. If I went from a starting point here to a starting point here, I got to write down the assumptions I got to walk through. So a lot of times thermodynamics can be that way. If you're taking this really for a class, go do it. Make sure you go through the homework. But honestly, there's a lot of computer libraries out there now that make this pretty easy. And so RefProf is when? RefProp. And it even has an Excel built-in. The one I like is actually called CoolProp, because it's got a Python module. And so I can do all my calculations in Python. I can make all of these graphs in Python. It's got a fairly decent library of liquids. And so I may show some examples of that, but that's really kind of the super useful way to go. And so I'm just going to finish this episode with just one of the examples that was there in the book, just to kind of highlight, like, what are we talking through all of this. So imagine you had a system here full of water, and you had some paddle wheel, and you're just turning the crank on this paddle wheel. And so if you've gotten this thing all the way up to vapor, to starting to boil, right, all the way to vapor, that the problem, an example was pressure versus volume, and then the question was, if somehow you already heated it up to this point. So let's say you added, put this under oven, and you've gotten this system at atmospheric pressure, so that's 14.7 psi, and you're still adding work to it. Now, because this is a box and the mass of the water is staying inside, nothing's coming out, and the volume of this box is unchanged, then really what that means is, as you keep turning the crank, you're actually going up on a constant volume line. So you're actually translating up, and the question is sort of, what does it take if you wanted to raise this pressure through just turning this crank to 20 psi? Okay, and so you can go through and do all those calculations, and the problem itself said things like the volume was 10 feet. Okay, and so you can look up, whether you're looking up at the back of the tables or you're calling sort of scientific value, like what is this specific volume here at state 1? Well, if you look it up, it is 26.8 cubic feet per pound. And so from that, you can actually figure out how much mass you have in the system. The mass is 0.373 pounds. And then, because you're doing a constant volume, because again, the volume of this box isn't fixed, then you actually know that's V2 is the same as V1, so that's great. And then you can look up what's U1, because you know the pressure and volume of this, and so you can get that U1 is 1077 BTUs per pound, and then U2, you then kind of finish off and look that up, 1161.6 BTU per pound. And so then if you go back to just conservation of energy, what are we looking at? So you have the change in internal energy plus the change in kinetic energy plus the change in potential energy is equal to Q minus W. So, not moving any faster, not changing anything. We're not raising it up as we're doing this experiment. And the point here is you might have been heating the water to get it to the starting point, but the idea in this example is that, no, from here on, you're just turning this thing. So there's no heat coming in, there's only work. And so you can go solve it. And ultimately, you find that it's U2 minus U1 times mass, and you would get the answer that this is minus 31.3 BTU. So you can run these calculations. And again, so think of all the poor grad students, all the scientists who have, tabulated this data for you, such that the problem was fairly well posed. Well, I started at 14.7 psi. I'm starting at, this is all been turned into vapor, so I'm on the line. Well, I can go look that up. So I can look up the specific volume of it. I can go look at the internal energy of it. And then in the process, go into state 2, all I was doing was just turning the crank. And so holding constant specific volume until I get to 20 psi, well, I can go look up, again, what the internal energy now is at this new state, based on, again, all these experiments people have done. It's all tabulated in the back of this book, or are you looking it up in your reference properties algorithm. And so now I have U2. So I have the change in the internal energy of the system. Nothing else is happening except for that work that I'm putting it in, and so I can solve for the work. So, and I'll just finish with, I know a lot of times units are weird. I mentioned units are, the point of units are for communication. BTU is an interesting unit, right? It's the British thermal unit. And, most of these units actually have some anchor point. So it's not too bad. And really, the British thermal unit is 1 BTU is how much it takes to do 1 pound mass of water and raise it by 1 degree Fahrenheit. And so, that works pretty well. So BTU is actually well defined. I know the SI lovers out there are going to want things like watts and Kelvin or centigrade. Right? Centigrade 0 is ice, is freezing point of water. 100 is a boiling point. Sure, I get it, but it's all a matter of right in the end communication. In the rocket and aerospace industry, yeah, we don't use BTUs. We may talk about PSIs in terms of pressure, but as soon as we're ever talking about things like heat fluxes or heat rates, things like that, we almost always will switch over to watts or kilowatts. Just the BTUs ones, it can get kind of complicated in some of the weird math. But again, the point of the units is communication. So you communicate in the industry you're in, and then when you're calculating, make sure you follow through and be diligent on the calculations. So see you next time.